Hello, my name is Patricio Morales-Priego, and today I'm presenting a DFT study on the structural, elastic, and electronic properties of gallium calcium bromide 3 halide perovskite. This study was conducted by the researchers listed on screen. Throughout this presentation, we'll go over the abstract, later on an introduction to the topic, and lastly, the results of the investigation, namely the structural, elastic, and electronic properties of the compound. At the end of the presentation, we'll go through the conclusions and references. Now, a theoretical study of the gallium calcium bromide 3 perovskite was first made by first principles density functional theory using the Castev code with the local density approximation using the CAPZ pseudopotential. The calculations were computed for the hydrostatic pressure range of 0 to 10 gigapascals, and the results of the calculated enthalpy suggest that the compound undergoes two back and forth phase transitions between the PM3M and FM3M crystal symmetries. Namely, we found that structurally, the lattice parameters decrease in both phases as the pressure is applied. We also found that for the elastic properties, there is a display in an increase and a decrease of the Pugh's criterion and Poisson's ratio, respectively. Besides, the electronic band structure shows semiconducting behavior. These were the results found in the study. As a quick introduction to the topic, we can talk about how recently metal halide perovskites of the ABX3 structure have recently attracted the attention of the scientific community due to their possible electronic applications, because of properties like adjustable band gaps, an elevated absorption coefficient, extended carrier diffusion lengths, and low exciting binding energy. They are also sought after for their structural properties like notable defect tolerance, high solution processing capability, and low processing temperature, which is in the range of 100 to 200 degrees Celsius. As for this study, we decided to work with gallium calcium bromide 3, which is illustrated in figure 1. And in this material, it's mainly present in the PM3M structure with its characteristic octahedra shown in B of the figure, and in C we can see the FM3M structure. The stability of the compound was first verified and then compared between the two most promising structures, which were PM3M and FM3M. The analysis of the formation enthalpy difference between these two structures is shown in figure 2. From this data, we can pinpoint two phase transitions with transition pressures of 2.5 and 4.2 gigapascals respectively. In figure 3, we show the most significant of the structural properties, which is the lattice parameter as a function of a pressure. You can see that as the pressure applied to the compound increases, its volume decreases, and consequently, its lattice parameter does so isometrically. This decrease is gradual up to the point in which the first transition occurs. The lattice parameter increases noticeably because of the natural increase in the crystal coherence as a result of the change in crystal structure. Despite this, the decreasing tendency of the lattice parameter is respected and holds for the later PM3M structure. For the elastic properties, we would like to present both the Pugh's criterion and Poisson's ratio as a function of the increase in pressure. We see a decreasing trend to the pressure range of the Pugh's criterion, where the starting value is less than 0.57, and it keeps on decreasing. This means, of course, that the material keeps on becoming more ductile. On the other hand, the Poisson's ratio grows above the 0.33 mark, and this represents a tough material, though incomprehensible, similarly to, for example, aluminum. Electronically, we found that the material showed a rise and fall behavior around the transition phase to the FM3M structure, as you can see here, computed as the band gap as a function of the pressure. On that note, we see here that the partial density difference of the states for each orbital per atom, as well as the total density of states. This is illustrated for the compound under 0 and 10 gigapascals. We can see both the band gap between the conduction and valence bands of the compound, as well as the main contribution per atom to set bands. The important part here is that the jaggedness of the peaks around the conduction bands indicates a growing metallicity in the compound as the pressure increases. And of course, this meaning a possible delocalization of the charges in the compound as a function of pressure. And to conclude, we'd like to say that formation enthalpy suggests stability for the PM3M and FM3M structures with two back and forth transitions pressures at around 2.5 and 4.2 gigapascals. Then that the structural compression was observed because of the increase in hydrostatic pressure of the compound. Also, that the elastic properties, namely the Puig's criterion and Poisson's ratio, imply a somewhat flexible, tough, but ductile material. Also, that the material has a changing band gap of around 2.7 electron volts, making it a semiconductor, and that the density of states and the partial density of states suggest the localization of charges as a function of pressure. We would like to give our deepest thanks to J.A. Antonio, R. Escamilla, and J.M. Cervantes for the opportunity to work with them at the Instituto de Investigaciones en Materiales. We acknowledge the following for computational resources, support, and technical assistance: the Laboratorio Nacional de Supercómputo, Centro de Supercómputo y Laboratorio Nacional de Supercómputo del Sureste de México. Thank you for your attention.